Before I begin my lecture, let me thank Mishra, my nephew, final year graduate, final year student of IIT Chennai, who has been very helpful in recording the lectures. We had in the last class discussed superposition of wave. We said that if a particle, ether particle of the medium is disturbed by a number of waves, the resultant displacement will be the vector sum of the displacement due to component waves. This is necessary because a particle, an ether particle, cannot be at two places at the same time. Now, for the interference phenomena, there are some conditions which should be fulfilled. The first one being the coherence of the wave. The wave should be coherent. And this is possible if two waves be derived from a single source. If we take two different sources emitting the light of same wavelength, they cannot be coherent because the emission of light depends upon the excitation of atoms, which vary with time in different manner for different sources. Secondly, the wave should have same or nearly same amplitude or frequency. For complete cancellation, the amplitude of the wave should be same and frequency should be same because the coherence also requires that. The third thing is that waves should be moving along same or almost the same line. This we can apply, the principle of superposition we can apply only when we have the waves traveling along the same line or almost the same line. And the last one, for maximum or brightness or constructive interference, the path difference between the waves should be N lambda. The path difference actually is the difference of path traveled by two waves originating from two coherent sources reaching a particular point P on the screen. This path difference should be N lambda, either should be lambda, 2 lambda, 3 lambda, which corresponds to the phase difference of 2 pi, 4 pi, and so on. And for minima, similarly, or darkness, we should have the path difference 2n plus 1 lambda by 2. This will give you path difference. The first one, if you put n equal to 0, you get lambda by 2. For n equal to 1, you get 3 lambda by 2, and so on. When this happens, the waves meet in opposite phase and cancellation takes place. Now, the first condition, the most essential condition for the interference to take place, coherent waves can be obtained from a given source by two methods. The first one is division of wavefront, in which the wavefront emitted from a source is split into two parts by reflection or diffraction, which travel different distances and they may reunite again to produce this phenomenon. And in this class of splitting, we have the Fresnel's biprism, experiment of Fresnel biprism and Lloyd's mirror. And the second method is division of amplitude, in which the amplitude of the incident wave is divided into two parts, which again travel to different distances, and this again can be done by reflection or refraction, partial reflection or refraction, and they travel different distances to reunite again to produce the interference phenomena. This is what happens in the case of Newton's ring and Michelson interferometer. Now, Young's double slit experiment that is talked about. Young's double slit experiment was a phenomenal experiment which actually confirmed the theory of matter waves also, because the manner in which the waves are being waves superimposed over each other coming out from two different sources, you can see, this phenomena can happen in the case of two electron beams also. And this experiment is in confirmation with the dual nature of matter and light. Young's double slit experiment performed by Thomas Young in 1801 actually as demonstrated here, we have a plane wavefront which strikes slits S1 and S2. Secondary wavelength, you know that every point in the primary wavefront is a source of secondary wavefront. So secondary wavefronts originate from sources S1 and S2, which superimpose over each other at different points on the screen. And you can understand very clearly that the point, central point on the screen, this is the screen, the central point on the screen, which is equidistant from the sources S1 and S2, the path difference here will be 0, and this point should be a point of maxima of brightness or constructive interference. And as we move along parallel to the screen, at different points you will observe that the path difference varies. The conditions of maxima and minima is satisfied alternately and will have alternate bright dark pattern, which we call interference fringes. An analysis of this has been done here. The figure for the analysis is over there. You can see this is the figure for the analysis. We have taken a monochromatic plane wavefront here. This is a monochromatic plane wavefront. The sources S1 and S2 behave as two coherent sources. The light originated from these two coherent sources reach any point, any arbitrary point P on the screen to superimpose over each other, and we will analyze what would be the condition of maxima and minima at any arbitrary point on the screen. And for the purpose, we have taken the separation between two slits, coherent slits, to be d, small d. Distance between the plane of the slit and screen, capital D. O is the central point on the screen. Waves from sources S1 and S2 reach the point P, which is at a distance x from the central point O on the screen. And these two waves superimpose over each other to produce interference fringe. Now we try to analyze at which point we will have maxima and at which point we will have minima. You see, the path difference we can calculate between two waves. Our aim will be to calculate the path difference originating from the source S1 and S2 reaching the point P on the screen, and then we'll apply the condition for maxima and condition for minima to know at which point we have maxima and at which point we have minima on the screen. We have taken these two distances as d1 and d2 respectively. See, you can observe here from the figure PQ equals x minus d by 2 and PR equals x plus d by 2. Can you focus at the figure, please? PQ equals x minus d by 2. Look at that. And PR equals x plus d by 2. d1 square will be d square plus x minus d by 2 whole square. Similarly, d2 square will be d square plus x plus d by 2 square. d2 square minus d1 square equals 2xt. And this we can take as d2 minus d1 times d2 plus d1 equals 2xt. And for if the point P be very close to O, we will see that d1 and d2 are almost equal, which will be equal to d in turn. And therefore we can utilize that fact over there. You can see d1 equals d2 equals d. And this will give you d2 minus d1 equals this. For this we can use 2d here. And d2 minus d1 we get as xd by d. This is the path difference we have calculated. The path difference between this, which is actually S2n. The path difference S2n we have calculated to be equal to xd by d. Now for maxima at the point P, the condition for maxima is path difference should be equal to n lambda. So maxima at the point P will be getting by using this condition, and this gives you x equals n lambda d by d. This x actually gives you the position of maxima on the screen measured from the central point O. And these positions can be obtained by putting n equal to 0, 1, 2, 3 and so on. If you put n equal to 0, you get x equal to 0, which corresponds to the central point in the screen, and this is the central maxima. For n equal to 1, you get x equals lambda d by d. On either sides of the central point O on the screen, will have the first order maxima at a distance lambda d by d. If you put n equal to 2, you get x equals x2, which is 2 lambda d by d. So on either sides of the central point O at a distance 2 lambda d by d, we will have maxima again, which is the second order maxima. Now the separation between consecutive maxima is known as fringe width. So fringe width, which we denote by beta here, this will be equal to 2 lambda d by d minus lambda d by d. This is lambda d by d. And yes, this is what we have for the fringe width. Then we find the position of minima. Position of minima is given by the condition path difference equals 2n plus 1 lambda by 2. The path difference xt by d equals 2n plus 1 lambda by 2. This is what we have used here. X will be equal to this. This equation gives you the position of minima on the screen, at which point we'll have minima. And for first order minima, we have n equals 0. Remember that first of all, for n equal to 0 in the case of bright fringe, we have central fringe. But we can have central fringe only bright or dark. Already we have obtained that the central fringe is bright, so we cannot have bright fringe at that point, dark fringe at that point. So this will be called first order. We'll be getting first order minima for n equal to 0. And this we get as x prime equals lambda d by 2d. For second order minima, we have n equal to 1, which gives you x double prime 3 lambda d by 2d. Fringe width beta will be again the difference of the two, which comes out to be lambda d by d. This is the fringe width. So in general, we are getting for fringe width same expression lambda d by d, which is the separation between either two consecutive bright fringes or two consecutive dark fringes. Now, we can observe that this fringe width beta depends upon wavelength of light used. It depends upon the separation between the plane of the slit and the screen, capital D, and depends upon small d, which is the separation between two coherent sources. Now, if you increase the wavelength of the light used here, the fringe width increases, number one. If you increase the separation between the plane of the slit and the screen, capital D, the fringe width again increases. If you increase the separation between two coherent sources, small d, the fringe width decreases. What in case you take a white light for the formation of fringes? If you take the white light for the formation of fringes, each color, which mainly we divide into 7 parts, will have its own fringe system. But the central fringe of each one will fall at the point O. Therefore, the central fringe will be bright, but the remaining fringes will be colored. What if the whole system be immersed in a transparent medium of refractive index mu? In that case, the fringe width will be given by beta by mu, where mu is the refractive index of the medium in which the system is immersed. Next we observe what happens if a glass sheet of thickness T is introduced in the path of one of the coherent waves. You will observe that optical part of this ray in which the glass sheet or any transparent sheet of transparent material is inserted in the path of one of the beam or one of the wave, the optical part increases. The optical part of this one becomes mu times T here, whereas this one remains as T in air. The refractive index of air is 1, and therefore the path difference between these two waves will be mu T minus T, which you can take as mu minus 1 times T, and therefore path difference which we have calculated earlier to be xt by d, we can put equal to this much. This gives you the value of x, and this is the point where the central fringe shifts. The central fringe does not remain at the same point, rather it shifts upward in this case. If instead you put the sheet in the path of the beam coming out of the source S2, the central fringe will shift downward. And the shift is given by this expression mu minus 1 Td by d. But you know that the fringe width beta equals this. So how many fringes will shift in the field of view? You will get this by dividing x by beta, which comes out to be mu minus 1 T by lambda. Let it be dismissed for today. In the next lecture, we'll talk about Newton's ring and Michelson interferometer.